Okay. So you know, first thing first is actually you need to understand some of the term kat sini, some of the keywords yang ada kat sini. PVN power of C, this is means that it is a polytropic. Okay, so switch right away to polytropic process. It is neither isobaric, nor isochoric, nor isothermal, not all of these three. And then you were given 350 kilopascal, which is your P1. Okay, and then you were given 0.03 m meter cube, so this is your V1. And then final volume of 0.2 meter cube, so this is your V2. So if you look clearly, dekat sini, this is the first one is 0.3, final one is 0.2. So what is actually happening here, it is an expansion. Okay, expansion. It is not a compression, it is an expansion. And you were given n is equals to 1.5. So this is your n, which is 1.5. Okay. So again, when we put the assumption, okay, this is an quasi-equilibrium process, right? And we know that kalau kita tengok example tadi ni, okay, example yang diberikan tadi ni, P1 V1 to power of n is equals to P2 V2 to power of n. So this is one example because we have this kind of equation, persamaan kat sini tadi, okay. So we know that P2 is equals to P1. Tadi kita katakan P1 V1 to power of n equals to P2 V to power of n. Then we'll be able to determine our P2. Sebab kita boleh calculate by using this particular equation. You just move V2 and then to power of n, calculate everything, you'll be able to get our P2, okay, which is equals to 20.33 kPa. This making more sense because this is an expansion. So sepatutnya when there is an expansion, P2 pressure kita akan berkurang. So kalau kita ikut graf kat sini, our initial graph supposedly 350 lah kat sini, state 1. Okay, 350 kPa. And then it will come to state 2, which is 20.33 kPa. And then there is an expansion, which is daripada 0.03 menjadi 0.2, which is 8. So this is, I should make a correction here. It's not supposed to be 15. So it's supposed to be 350 kPa. And then at this particular temperature, pressure, it should be 20.33, which is similar like this. Okay. And then we have the, we want to determine the moving boundary work. So moving boundary work, kita tahu when we integrate this particular form, for the polytropic process, finally you will be able to get this equation. Okay, so that's why it is very important for us to determine the P2 first. But kita nak pakai dalam moving boundary work punya equation. So P2 V2 minus P1 V1 divided by 1 minus N. So when you substitute everything here, 1 minus 1.5, you'll be able to get the work, boundary work is 12.9 kilojoule. Okay, and you can see that it is a positive sign, it is not negative. So which means that the positive sign indicates the work is done by the system. Maksudnya the compression too is actually pushed by the gas inside the system. The gas pushing it, so that's why it expands. Okay, so you will be able to get positive here, right? So that is how example 4 being made. So let's move to example 5. Example 5 lah, it talk about a frictionless, ada perkataan kat sini, frictionless piston cylinder device initially contains 200 liter of saturated liquid refrigerant 134A. The piston is free to move and its mass is such that it maintains a pressure of 900 kilopascal on the refrigerant. The refrigerant now heated until its temperature rise to 70 degrees Celsius. Okay. So calculate the work done during this particular process. So there are the few keywords yang kita kena capture dekat sini. The first keyword is, okay, it's using liquid refrigerant 134A. Then we know that, okay, table mana yang kita kena refer is actually table A11 and A12, right? until A13 if not mistaken. Okay, table 8 and 811 until A13. So this is something got to do with liquid refrigerant, and it is saturated liquid. Okay, so if it is saturated liquid, we know that straight away. If it's saturated liquid, we know what will be the saturation temperature, what will be the saturation pressure, because this can be obtained from the property table. Okay, dia memang is a universal value. Okay, dalam property table, kalau kita tengok saturated liquid, we will be able, saturated liquid for this refrigerant, it is consistent value yang kita akan dapat kat situ. Okay, and then kita nak tengok pula what is other keywords kat sini. Dia kata the piston is free to move. Okay, piston is free to move. Maksudnya kat sini it's not a rigid tank. So kita kena rule out this is not isochoric. Maksudnya volume dia berubah. Volume dia akan changing. Okay. And then the refrigerant is now heated until its temperature rise to 70 degrees Celsius, which means that temperature dia berubah juga daripada saturated liquid temperature menjadi 70 degrees Celsius. Okay. Apa yang tak berubah kat sini? It maintains a pressure of 900 kilopascal. Itu yang dimaklumkan tak berubah. So pressure tak berubah. So this is considered as isobaric process lah. So now the requirement is actually to calculate the work done during this particular process. Okay, saya ada masalah sikit. Stuck. Okay. I have my screen freeze. Tak boleh nak tak boleh nak gerak. Okay. Okay. Jumpa dah tapi okay, saya dah jumpa. I don't know what's the problem. Okay. Ya Allah. Okay. Okay. Moving to the solution of this example 5. Okay, sekarang ni again assumption kat sini the process is a quasi-equilibrium punya process. Okay, and then you know that the PV diagram that you should refer to is actually R134 punya PV diagram. Okay, and you know that the pressure is meeting constant which is at 900 and the point is actually at saturated liquid. Okay, so it is at saturated liquid. So this point of saturated liquid at 900 kPa, kita boleh dapat value dia, kita kena refer kepada table A11. Okay. And then you heat it up until it reach 70 degrees Celsius. But the pressure is maintained at 900 kilopascal. Okay. So here, when you want to get P1, okay, it is 900 kPa. Kita akan dapat our V1, specific volume of V1 is V at of saturated liquid at 900 kPa. If you refer to table A11, okay. So if you refer to the table A11, saturated refrigerant temperature table, it's supposed to be table A12. Okay, table A12. Then you look at the pressure is 0.9, which is 900 kilopascal. You'll be able to get this particular value 0.008580. Okay. So lepas tu kita kena tengok pula dekat 70 degree Celsius. Okay. And then we go to table A13. If you want to go to table A13, alright, because this is superheated refrigerant, is you'll be able to see that at temperature as 70 degree and 900 kilopascal, which is 0.9 megapascal, then you also be obtain some value of V, which is equals to 0.027413. Okay, so this value, this is where you get from table A12, and this value is where you get from table A13. Table A13. So you got V1 and V2. So the boundary work is determined from its definition to be M is equals to V1 over specific volume. V1 ni V huruf besar, the V1 yang bawah ni ialah huruf kecil because this is specific volume. Then you'll be able to get the mass of the refrigerant, which is equals to 233.1 kilogram. Right? Sebab kita tahu in order for us to determine V1, okay, it is should be multiplied with M multiplied with V1, which is V1 ni ialah specific volume. Yang ni yang kita dapat from property table. Okay, this V1 is from the property table, and then we multiply with the M. But now M is unknown, but V1 is something that we know because V1 is actually 200 liter. Okay, also equivalent to 0.2 meter cube lah. So when we rearrange back the equation, we should be able to get mass is equals to V1 over V1 lah. Sebab this is meter cube, cancel with meter cube, then you'll be able to get in kilogram. So you get your mass as 233.1 kilogram. And you know that in order for us to determine the, if you look back at this scenario, okay, this is just another rectangle lah. Okay, this is just another rectangle. So we just actually measure area under the curve, but we have to be careful because this is a specific volume. It is not what we call as volume yang betul-betul of the tank. Okay, volume betul-betul of the tank kita dah diberikan sebagai 200 liter tadi, but it's not being put here because PV diagram kat sini ialah P versus V, small v, which is specific volume. So that's why kita kena tahu what is the mass. So when we multiply with the mass, only then you'll be able to get the real. Okay, so we still stick to this equation integral. Okay, P dV V2 minus V1, and then in order for and we know the mass already, we take out the mass, multiply with P, multiply with V2 minus V1. So V2 ni kita dapat daripada sini, which is from table A13. Okay, and V1 tadi kita dapat kat sini, which is from table A12. Okay, so when we substitute everything, then you got the moving boundary work is 55071 kilojoule. It is a positive sign, so it indicates the work is done by the system. Okay, because this is what we call as this is an expansion lah. Maksudnya daripada V1 dia jadi V2 kan, so it is expanding. Right? So this is example 5. So let's have a look at example 6. Just so you know that actually I have another chapter sebenarnya. So tapi sebab because my time has reached, okay, what I'm gonna do is actually I'm going to record the video for that chapter so that you'll be able to have a self-learn. But I think it's very related dengan apa yang Dr. Anis Atikah akan ajar nanti. So you can have a look at the video later, and then lepas tu, and it makes sense lah to what actually Dr. Anis Atikah will cover as well. Right, so for example 6, a mass of 2.4 kilogram of air at 150 kilopascal and 12 degrees Celsius is contained in a gas-tight frictionless piston cylinder device. Okay, so look at this statement again. A mass of 2.4 kilogram of air. So maksudnya kita diberikan air sebanyak 2.4 kilogram. Okay, 2.4 kilogram of air. Okay, this is M. And at 150 kilopascal, so this could be considered as P1, and 12 degrees Celsius is contained in a gas-tight frictionless piston cylinder device. So what does it mean by frictionless? Okay, dekat sini which means that bila kita ada piston ni, frictionless ni dia tak ada friction, dia tak tersangkut-sangkut. Maksudnya dia boleh senang je freely move, sama ada dia freely expand or freely being compressed. Okay, dia tak sangkut-sangkut. So kat sini juga kita boleh cakap sebenarnya this is related to quasi-equilibrium. Okay. So the air is now being compressed. So sekarang ni tadi kita ada 2.4 kg dekat 150 kilopascal. So now kita nak compress daripada 150 to become 600 kilopascal. Okay. During the process, heat is transferred from the air such that the temperature inside the cylinder remains constant. So what is the keyword here? This is an isothermal process. So when isothermal process, kita tahu kita kena go back to the curve lah. Curve yang macam ni tadi lah kan. So kita ada V1, kita ada V2 and kita ada P1, P2. So P2 will be higher. This is a compression process. Okay. And it's moving toward this direction. So kita kena guna term yang ln tadi lah. Ln V2 over V1 dan sebagainya tadi. So calculate the work done during this process. Okay. So from here, the process, okay, kat sini kalau tengok balik dia punya assumption dia, the process is quasi-equilibrium process. Air is an ideal gas, okay, and the gas constant of air is R equals to 0.287, yang ni kita boleh dapat dari table, okay, and the boundary work is determined from its definition to be, okay, kita tahu daripada isothermal process, when we integrate this, we are gonna have P1 V1 ln V2 over V1. And we can actually simply replace V1 dan V2. Kita tak diberi maklum what is V1, V2. Tapi because we know that P1, V1 is equals to P2, V2. Kita boleh simply replace, okay, V2 over V1 is equals to P1 over V2. Kita boleh replace kat sini. So V2 over V1 is actually P1 over V2. So kita masukkan value tu kat sini. And then we know what is R because R is a gas constant. We know what will be temperature. Temperature must be in Kelvin. So you have to be careful. Dalam gunakan equation ni, you have to make sure that temperature is converted into Kelvin, which is tadi 12 degree plus with 273 K Kelvin. Okay. And then multiply with the mass. And then you put in the ln. And then you'll be able to get negative 272, which means that it's a compression, work done to the system. Okay, work done to the system is not by the system, but it is done onto the system. So you'll be able to get this. Okay, nampak tak? So it's not that difficult pun sebenarnya. Okay, dia jadi pula. So let's have a look on another example. Jadi example 6 kita dah cover. So now let's have a look at example 7. Example 7, okay. You were given nitrogen at an initial state of 300 Kelvin, 150 kilopascal, and 0.2 meter cube is compressed slowly in an isothermal process to a final pressure of 800 kilopascal. Determine the work done during this particular process. Okay, so here you can see that there is a change, significant change from 150 kilopascal becoming 800 kilopascal. So this is a compression work. And you should know that the volume daripada 0.2 dia akan jadi lebih kecil. V1 akan jadi lebih kecil. And this is, they mention straight away here, it is an isothermal process. So you know that 300K here will be constant. So when 300K is constant, we know that the equation that we should be used is the ln tu lah. Maksudnya kan work done is equals to P1 V1 ln V2 over V1 tadi. Alright. So the assumption again, the process is quasi-equilibrium. Nitrogen is an ideal gas. So straight away we use this particular equation P1 V1 ln V2 over V1. Okay, and then we can substitute V2 over V1 because we do not know the volume, but we know the pressure. Both pressure we know it. Then we put ln 1 divided by P2, P1 by P2. We substitute and then we got the negative sign, which means that it is indicate the work done into the system. Okay. Right. So the most important part when actually we do the energy analysis is actually for us to do energy balance. Energy analysis ni penting kepada kita when we do the study of the thermodynamics ni. It needs one important thing that we need to do is actually what we call as energy analysis. You will learn more about energy balance ni when you take the next semester punya course, material and energy balance. Okay, but for now, what happened is you should also remember, okay, kita kena ingat balik pada sistem kita. If you can write it down at the chat section, berapa jenis sistem yang kita ada? Apa sistem-sistem tu? Anyone can write it down. What are the type of system that we have? If you can remember, if you can recall. Okay. Anybody can write it down at the chat section. Kalau tak ada siapa tulis, okay, Lavinia George, thank you. Tidak, baru ingat kalau tak ada siapa tulis, tak tahu nak start quiz ya. Okay. Okay, so we have isolated, closed and open system. Right. So for isolated system, we couldn't do the energy balance. We couldn't do the mass balance for it because it is an isolated system. There is no heat transfer. There is no mass transfer. Okay. So the example of isolated system macam flask lah, which is actually you contain it is a vacuum flask. There is no heat being transferred in or out. There is no mass that could go in and out. But now we are interested to look at the energy balance for closed system as well as the open system. Okay, so for the chapter 5 that I will record later is on the open system, but this one we are going to look into the closed system. For closed system, okay, we actually have more terms kat sini sebenarnya, tapi it has been simplified because what we are interested to look at is actually we know that principle of the energy conservation. Okay, energy cannot be created or be formed, or it also cannot be destroyed, but energy can transfer from one to another form. Okay, energy can transfer from one form to another form. So here what we can do is actually we can calculate the energy balance. The energy balance, okay, energy in, whatever the energy is supplied in minus energy out, you will have the change of what we call an energy system. So the net energy transfer by heat, work and mass is equals to the change of energy in the internal kinetic potential and so on. So this is given in the kilojoule punya ni lah, energy is kilojoule. But when you put a dot over here, this is what we call as energy rate. The rate, okay, the rate ada kat sini, which is respective with time. Okay, dE system divided by dt. A rate of net energy transfer by heat, work and mass is equals to rate of change in internal kinetic potential and so on. So this is what we call express the energy balance in the rate form. This is energy balance per unit mass, okay, when this is divided per unit mass. And for a cycle, we have the work net out is actually the heat net in, ataupun kalau dalam bentuk rate, the rate of work being transferred out is equals to the rate of heat transferred in. So this is energy balance for a cycle. What also written here is that the first law cannot be proven mathematically, but no process in nature is known to have violated the first law, and this should be taken as sufficient proof. Okay. So when we want to do an energy balance for a constant pressure process. Okay, Peter. Okay. Right. So when we want to do energy balance for a constant pressure, expansion or compression process. Okay. Constant pressure, expansion or compression process. The keyword dekat sini yang kita kena tahu ialah constant pressure. Okay, constant pressure process. Which means that pada awal-awal pressure dia sama sampai pressure towards the end. So the general analysis for a closed system undergoing a quasi-equilibrium constant process. Okay, so this is the general analysis. This is the general equation that we can use. Q, the heat is being to the system and work is from the system. So this is kalau kita kata macam expansion or compression, Q tu means the heat, heat being provided to the system, and work is actually coming up from the system. So when we have the equation, kalau kita tengok balik equation pada awal, energy in minus energy out. So this is actually Q minus W. Okay, Q, which is the energy in, work is the work out. Okay, and the change of the system here is actually the change of U plus delta KE plus delta PE. But, okay, there is a but, this is a closed system. So when it is a closed system, kita boleh omit actually the change of kinetic energy and the change of potential energy. What is actually changing is just the internal energy. Okay, so imagine there is a closed system. Imagine tadi kita ada closed system. It's not necessarily adiabatic, tak semestinya adiabatic. Tapi kalau kita kata kita ada mass kat dalam ni, kita ada mass kat sini, and then kita ada some of the heat. Bila kita kata kita ada closed system, okay, closed system, the mass kat dalam ni dia tak boleh pindah mana-mana. There is no mass transfer, it is just the heat transfer. And there is some energy being transferred here. So let's say lah kita melakukan pemanasan. So the energy being transferred is 15 kilojoule. Okay. And then there is a mass here, absorb some heat. Okay. Daripada tak ada heat, they absorb some heat. But it's also at the same time, because it's a closed system, there is also some heat can be transferred out as well. So let's say that the heat transfer out is 5 kilojoule. Okay. You cannot say that the heat transfer out 20 kilojoule. Doesn't make sense because what you supply here is only 15 kilojoule. Okay. So what you're trying to put inside here, so if let's say you put energy in is 15, okay, energy out is 5, so you know that 15 minus 5, whatever left in the system is 10 kilojoule. So where is actually 10 kilojoule? Dia ada dekat dalam mass ni. Okay, dia ada dekat sini, dalam ni, which is 10 kilojoule. What is that 10 kilojoule? Is actually the change of the internal energy. Okay, the change of internal energy kat sini. Right? So when we actually simplify further, okay, expand further the equation, kita akan dapat Q minus work other plus minus with the boundary work, then you'll be able to get U2 minus U1. Okay, boundary work ni essentially that if you add up together, kita akan dapat macam ni lah. Maksudnya kita put in a bracket, Q minus work is equals to U2 minus U1, tapi dalam work itself, dia ada dua jenis. One is the work that is being done by others, such as shaft work, rotating work, whatsoever. And there is another work that is being done, what we call as boundary work yang kita calculate tadi. Okay, and this is equals to U2 minus U1. So when you simplify further, you know that WB is actually a product of P multiplied with V, right? And then if it a constant pressure, it is P naught lah. P naught V2 minus V1 macam tu. So that this is what actually you substitute back dekat equation kat sini. And you maintain U2 minus U1 kat sini juga. Okay. So work other again, you maintain it. If let's say this is a shaft work, rotating work and so whatsoever, this is work other. So Q minus W other, work by other work, is equals to U2 plus P2 V2 minus U1 plus P1 V1. Ni kalau kita rearrange back the equation, and we should know that enthalpy is equals to U plus PV. Okay, so when we further rearrange back this equation, then you'll be able to get Q minus work others is equals to enthalpy change of the state. H2 minus H1. Okay, H2 minus H1. So, for a constant pressure expansion, so ini untuk valid cuma kepada constant pressure. Okay, so if let's say you have a constant pressure expansion or compression process, okay, you'll be able to use this particular work. constant pressure, you will be able to use this particular equation. Delta U plus boundary work is equals to delta H. So that's why kita boleh substitute delta H masuk dekat sini tadi. Okay. Ini untuk constant pressure saja. Yang mana kita ada P naught. Maksudnya dia tak berubah. Walaupun kita ada expansion atau ada compression, the pressure maintain the same. So an example of constant pressure process. So we have work in, okay, minus Q out minus boundary work, then you'll be able to get delta U. And then when you rearrange back the equation, delta U plus work, boundary work, you'll be able to get delta H. And delta H, in order for you to determine it, is simply mass multiply with the change of the enthalpy. Okay, kat mana value kita boleh dapat change of enthalpy ni? Sometimes if let's say if you're using water ataupun using steam, saturated steam ke whatsoever, we can refer to the property table. Mass is something that we need to know lah. If it's given, kita boleh calculate. If it's not given, we need to determine lah. So that is the example of using the energy balance for a constant pressure process. Okay, so again, if you put the system kat sini and pressure is constant, whether it is a compression or whether it is an expansion, the pressure, if the pressure maintain constant, so we can actually substitute everything, boundary work and delta U, and it is replaced by the change of enthalpy, delta H. So note that this relation is not valid for closed system processes during which pressure does not remain constant. If let's say the pressure pada awal 100 kPa, pressure lepas tu 105 kPa, this particular equation is not valid. We must make sure that the pressure is maintained the same. Okay, let's have a look at the example. A fixed mass of saturated water vapor in piston cylinder at 400 kilopascal is isothermally cooled until it is a saturated liquid. Okay, calculate moving boundary work in kilojoule per kilogram and amount of heat rejected during this particular process in kilojoule per kilogram. So this is where actually kita tengok balik apa yang important punya parameters kat sini. Okay, a fixed mass. Okay, a fixed mass. Bila dimaksudkan kat sini a fixed mass, mass tak berubah, tak pergi mana-mana. Okay, this considered could be a closed system. Okay, this is a closed system. And it is a saturated water vapor. Bila kita dapat kataan saturated ni, you know that, okay, I should refer this to the property table. Okay, I know I should refer to property table, so I could know what is the saturated vapor at 400 kilopascal. Okay, is isothermally cool until it is a saturated liquid. So kat sini dia kata it is a saturated water vapor and then isothermally cool, which means kat sini juga temperature dia tak berubah. Okay, so kat sini kalau saya dah terbayang, if I start to draw it, okay, I should draw a PV diagram. Okay, a PV diagram, and then I should imagine that at 400 kPa, okay, and they said it is a saturated water vapor. So saturated water vapor is at this particular line kat sini, and it is being isothermally cool, which means that dia akan cool sampailah dia dapat saturated liquid. So this is 0.1, this is 0.2. So what happened is, kalau kita tengok volume, this is V1, this is V2. So there is a somehow of compression lah. Tapi compression yang berlaku, the volume is actually the change of the volume tu berkurang, tapi pressure dia tetap sama. It maintain as 400 kPa. So now calculate the moving boundary work in kilojoule per kilogram. So how do we calculate the moving boundary work? It's easy. Okay, we just need to determine the area under the curve. But we need to know what will be the, because this is specific volume, so we need to know the volume itself. Okay, what is V? Right. So, and then the amount of heat rejected during this process. So this is where actually we need to do some kind of energy balance as well. So let's have a look at this solution. So the assumption, the the cylinder is stationary and thus the kinetic and potential energy changes are zero. Maksudnya cylinder ni tak berubah apa-apa. So there is no kinetic and potential energy. There are no work interactions involved other than boundary work. Kat sini tak ada shaft, tak ada rotating, tak ada stirrer whatsoever. So there are no work interaction other than the boundary work. Maksudnya the boundary work tu ialah perubahan daripada expansion ke ataupun compression work. Okay. The thermal energy stored in the cylinder itself is negligible. The compression or expansion process is quasi-equilibrium. Okay, so we take the contents of the cylinder as the system. This is a closed system since no mass enters or leaves. The energy balance for this stationary closed system can be expressed as follows. So we use because this is a closed system, stationary closed system. Okay, the keyword kat sini, this is a stationary closed system. And then you know that we're going to use this particular equation. And this is a constant pressure. Okay, since this is constant pressure and the kinetic energy, potential energy is equals to zero. So we simplify this, become negative Q out minus work boundary out plus mu2 minus u1. But we know that this expression for a constant pressure, okay, W B plus with the change of the internal energy, you'll be able to get the change of enthalpy. So this is simply a change of enthalpy is equals to M multiplied with the specific enthalpy at state 2 minus specific enthalpy at state 1. And rearrange back, you'll be able to get this equation. And then when you get the Q out minus equals to H1 minus H2. Q out ni is a specific heat lah kan? Specific heat. Right. So this is a during constant quasi-equilibrium process. So how do we get the Q out? Q out ni kita kena refer dekat table balik lah. We go to property table. Kita tengok dekat saturated vapor phase at 400 kPa, berapa value dia. Kita tengok dekat saturated liquid at 400 kPa, berapa enthalpy dia. And then you'll be able to get the change of enthalpy, HFG, which is equals to Q out. Then you'll be able to get 2133.4 kilojoule per kilogram. So, and we note that the temperature also remain constant and the saturation temperature at 400 kPa is 143.6 degrees Celsius. Okay. So if you know the mass, okay, kalau kita tahu mass, then be able to know what will be the energy rejected kat sini. And then kalau kita nak tahu, kita tahu juga mass. If you know juga the mass, okay, once we are informed the mass, we can also determine what will be the moving boundary work kat sini. Another examples that I would like to share with you on example 9. A rigid 0.01 meter cube vessel. Okay, bila perkataan dengan perkataan rigid ni kita dah tahu dah. Okay, this is what kind of processing? It is isochoric, which means that volume tak berubah. Okay, the volume tak berubah. Volume V1 ke V2 ke sama kat sini. Containing a mixture of liquid water at 100 degrees Celsius. Okay, liquid water at 100 degrees Celsius with 12.3% quality. Okay, so the term come here ialah 12.3% quality. X is equals to 12.3. Macam mana X equals to 12.3? Kita kena ingat juga 12.3 ni macam mana dia dapat ialah mass of the vapor divided by the total mass. So the mixture is then heated until its temperature is 150 degrees Celsius. Calculate the heat transfer required for this particular process. So we go back to this particular equation in order for us to do the energy balance analysis. So energy in minus energy out equals to the change of the system. And what we can do here is we know that there is energy in, Q in is equals to change of internal energy and is equals to mu2 minus u1 because KE and PE is equals to 0. Okay. is there any change of pressure? There is, okay, if you're looking at the V diagram, okay, at this particular state, this is at 100 degrees Celsius, okay. So imagine there is a straight line kan, straight line, dia ada saturated liquid kat sini, saturated vapor kat sini, tapi dia actually kat tengah-tengah because dia ada mixture of liquid and gas, mixture liquid and vapor. So this is where X is equals to 12.3. Now it is being heated up to the point where it reach 150 degrees Celsius. Okay. So how do we determine the property of this? So kita kena tengok balik dekat table lah. So if you're going for saturated liquid, okay, we use this particular equation. V1 is equals to Vf plus XFVG. X ni is 12.3 tadi lah, 0.123. VFG we can calculate, memang ada dalam table E4 dah diberikan pun, okay, we can calculate VFG. And then VF pun value dia kita boleh dapat daripada table E4. And then at the same time we can also know what would be the specific internal energy for this. Okay, so we can also obtain from table A4. And then we have the specific volume. We also have the specific internal energy at X equals to 0.123. So now the temperature is actually becoming 150. And we know one thing, that it is a rigid tank. So rigid tank sepatutnya specific volume tak berubah. Okay, specific volume tak berubah. So once we obtain the specific volume for at 3 equals to 100, we can also make it equals to V2, which is equals to 0.2066, okay, which is the same because it is a rigid tank. So from here, okay, we can calculate our new quality for X2. So kita akan dapat the new quality which is equals to 0.525. So which means that ada 52.5% of liquid dekat 150 degree already becoming vapor, okay, already becoming saturated vapor. So from here you can also calculate your U2, which is UF plus X to U. And this is also the properties where you can get from the property table, and you'll be able to get this particular change of internal energy, okay, specific internal energy. And in order for us to determine the mass of the system, kita tahu kita diberikan the volume of the rigid tank is 0.1 meter cube, which is 100 liter tadi, and we divide by V1, which we already predetermined earlier from the table, then this is the mass of the system. So when we substitute inside it, okay, when we substitute, we put the mass, and then we know what is U2, we know what is U1, okay, and then straight away we'll be able to determine the energy that is being transferred. So what does it mean? Of 46.9 kilojoule ni ialah energy yang diperlukan to heat up, okay, energy that is needed to heat up the mixture of the vapor and liquid at 100 degrees Celsius with 12.3 quality to 150 degrees Celsius. So this is the amount of energy that you use to heat up from this particular state to become state number 2. So this is the amount of energy needed. Okay, I hope that later you can revise back this video, try to relook back how you can solve this particular problem. Sebab kat sini you need to really understand clearly how can you simplify daripada this energy balance going back to this. Okay, kenapa dia tak ada energy out? That is one question that you can ask. Okay, kenapa dia terus delta U is also another question you can ask. Kenapa actually tak ada kenapa you tak pakai expression yang delta H equals to WB plus delta U tadi? Kenapa tak pakai ini? So benda tu you need to rethink balik, look back from the previous example and look back from the previous equation that I have shared with you and try to make sense of this calculation. Okay. Example 10. Okay, ada satu lagi example, and then we talk about specific heat. Alright, tak apa, yang problem 1, problem 2 tu saya tak akan cover lah. Nanti you can have it on your own. Example 10. A piston cylinder device contains 25 grams of saturated water vapor that is maintained at a constant pressure of 300 kilopascal. So again, we come to the word here, which is constant pressure. And then kita ada piston cylinder device, ada 25 gram of saturated water vapor. So kita tahu, if you go to 300 kilopascal, then you be able to get the saturated water vapor property lah, information. Sama ada kita nak tahu dia punya specific volume, okay? Kita nak tahu dia volume, kita nak tahu internal energy, kita nak tahu dia punya enthalpy, so we can calculate from here, right? We can get from the table lah, right? At 300 kilopascal. A resistant heater within the cylinder is turned on and passes a current of 0.2 ampere for 5 minutes from a 120 volt source. At the same time, a heat loss of 3.7 kilojoule occurs. Show that for a closed system, the boundary work, WB, and the change in internal energy, delta U, in the first law relation can be combined into one term, delta H, for a constant pressure process. Determine the final temperature of the steam. So this is some kind of calculation that is being quite here. Okay. So let's have a look at how we solve this. First of all, we're going to use back the equation. Okay, energy in minus energy out equals to the change of the system. And then when you put the energy in minus energy out, you put this particular equation, Q minus W is equals to delta U plus delta KE plus delta PE. And you know that W is actually a compress of work by others, such as shaft work and so on, and boundary work, and it is equals to U2 minus U1. Alright. So for a constant pressure process, the boundary work is given as WB equals to B0 B2 minus B1. So when you simplify it further, and when you substitute this into the other side, then you'll be able to get H equals to U plus PV, and finally Q minus that work by others is H2 minus H1, which is delta H. So that's already proven for you because it is a constant pressure process. So to find T2, we need other property. Work is only electrical work, which is determined from, okay, kita tahu that in order for us to determine the work of the electrical, VI multiplied with delta T, okay, because kita tahu kalau delta T divide by work, okay, if let's say WA divide by delta T, this is actually equals to power, okay, which is expressed in watt. Power is also equals to VI, which is the volume, voltage multiplied with the current, okay. So in order for you to get the work, it's actually work of the electric is actually VI multiplied with the delta T, so that you'll be able to get the work done by electrical work, which is WE. Okay, so you got 7.2 kilojoule. At P1 at 300 kilopascal, you know that you got your H1 value, which is the saturated vapor at 300 kilopascal. This is the enthalpy, the specific enthalpy at that particular point. So when we apply in the equation in A, okay, we know that the electrical work in, okay, which is the electrical work by the electric, and minus Q out. Q out ni kat mana kita dapat? Because it was being informed earlier. It was informed earlier that there is a heat loss of 3.7 kilojoule occurs. Okay, so that's why we got 3.7 kilojoule here equals to delta H, and this is equals to M mass multiplied with H2 minus H1. What is M? M is given as 25 gram. Okay, this is already given here, 25 gram. And then you have H2 minus 2724.9. Okay, we didn't know what is H2, but we can already obtain from here. We already have the work in, Q out, and we can actually determine the specific enthalpy. Okay, because the question asks actually determine the final temperature of the steam. So we know H2 is 2864.9 kilojoule. This is at constant pressure. So if you're referring to table A6, try to look at 300 kilopascal and 2864.9 kilojoule, then you'll be able to get the temperature is actually 200 degrees Celsius. So that is your final temperature. Okay. So that's how the calculation being made here lah. Okay. Sempat juga nak cover, kena buat video lain. So I think I'll be talking about this in the next video lah. So this should end actually my lecture with you, but I'll be giving you the video later lah. There is one video covering this part on the specific heat, and then there will be some other chunk of videos that I'll be giving you because I'll be talking about chapter 5. Chapter 5 ni pula is actually doing energy analysis for the control volume. Dan ini for the closed volume. I'll be talking about control volume. Control volume kat sini dia akan ada term mass transfer juga. Sebab kalau dalam closed volume, kita just talking about energy transfer. Tapi kalau dalam mass volume, dalam control volume later on, I'll also be talking about the mass transfer. So ada term yang barulah dalam equation energy balance equation tu yang kita kena calculate nanti. It's okay. So right now I think I shall stop here so that we can actually start with our quiz. Do you have any question before I start the quiz? Is everyone here? Semua ada kat sini ya? I'll stop share for now. So I do the setting for the quiz. Okay. Okay, wait for a while. Okay, this is the instruction for you to go to quiz. So right now, I have shared with you the link so that you can go there. Socrates, https p.socrates.com. Okay, so when there is they require the room name, what you have to do, okay, you have to type KRD room. Okay, when there is a request of the room name, you type KRD room. Okay, when it requests you to enter your name, please write your name. Okay, for example, Haikal Jamil. Write down Haikal Jamil with your ID at the end without space. So if let's say you have ID 100,456 and then type something like that. Okay, so I know who's actually attempting the question and with the ID. So that's how you write it down. Okay, without space, just write it together with your ID as well. Okay, and then you can click done. Once you click done, then you can start answer. I'm giving you the room is open for 33 minutes. So we open at 6:27 right now. I shall close the room at 7 o'clock. And I mentioned to you, as I mentioned earlier, if you answer it right, you get 1 point. If you answer it wrong, you get minus 0.5. If you, for you to be safe, if you do not know, just answer no idea. Okay, so in all questions, ada 10 questions, if you do not know, and you answer no idea. So you can start now. Okay everyone, kita ada 17 minit lagi